Parabolas have some interesting geometric properties that make them very useful in applications. So here I have a parabola together with its focus here. I have the focus labeled F, and this vertical line is actually the directrix for this parabola. Just to verify that this really is a parabola with this focus and directrix, we can use the defining property of a parabola, which is that for any point on the parabola, which point A up here is going to be our stand-in point, for any point on the parabola, the distance from that point A to the directrix, which is this line segment right here, is an equal length to the distance from the point A down to the focus, and that's this distance here. You can see for this particular point, these two distances are the same. They're about 3.84, rounded to 2 decimal places. And if we move this point along the parabola, those distances will change, but they'll always be equal to each other. So way out here, they grow all the way up to 9.14. In between the focus and the directrix, they're much smaller, 1.3, 1.92, but always these two distances are the same. And that's how you can be sure that this curve really is a parabola. I have this set up so that even if we move the focus, the parabola will adjust itself to still be the correct parabola for this focus. So if we move the focus over here, these distances are still equal to each other. Notice that when I move the focus, the directrix also has to move in order to keep the vertex of this parabola at the origin. So if I move the focus further out, the parabola gets wider. If I move the focus further in, the parabola gets narrower. Okay, so what is this interesting geometric property about the parabola that I am referring to? Well, imagine that we have a light ray. Actually, let me hide this one. Imagine we have a light ray coming in from the right and hitting the parabola at the point A. So that would look something like this. Okay, so if this parabola is actually a mirror, this light ray is going to bounce off of this mirror. And the question that I want to ask is, where is that light ray going to bounce to? Well, to know how this light ray is going to reflect off of our parabolic mirror, you have to know a little bit about how waves, like light or sound, reflect off of surfaces. And if you ask a physicist, what they will tell you is if you draw the tangent line at the mirror surface, and you measure the angle where the angle at which the light ray is striking the mirror, like this, so it looks like here it's about 47.64 degrees, the angle that it reflects off of the mirror is going to be the same 47.64 degrees. And if you draw the outgoing light ray after it's reflected, it turns out that it goes directly to the focus. And this is actually true no matter what point A we choose on the parabola. If we slide it up here, the incoming light ray, as long as it comes in parallel to the x-axis, it strikes the mirror at some different angle. It leaves at the same angle, which is different than before, but still 32.04 degrees, the same as the incoming angle, and also goes through the focus. If we move this point right further down the parabola, those angles both change, but they change together, so they stay the same, and the reflected light ray still goes through the focus. In fact, that's why the focus is called the focus. It's because the focus is the point where all incoming light rays, again, as long as they're parallel to the x-axis, all incoming light rays get focused by the parabolic mirror onto the focus. So let's have a look at several of these light rays all at once, just to get a feel for how they look all together. So here, this blue curve is our parabola, which we're imagining is a reflector. Again, we have a focus and our directrix, and if we move the focus around, the parabola and directrix track to follow the focus. So here are a bunch of incoming light rays, and if we draw how they all reflect, they all go to the focus, like that. And if you look at any single intersection point here, where one of these incoming rays reflects off of the parabola, you can see just by estimating it by eye that the incoming angle at this reflection is equal to the outgoing angle at this reflection. And for the parabola is the special shape that makes all of these reflections all go to the focus. This is useful in applications because, well, if you want to see something very dim, too dim to see with your naked eye, what you need to do is gather up a lot of light and focus it all into one place. But that's exactly what a parabola does. So if you need to, for example, make a telescope to gather up a lot of starlight, you want to make a mirror that is in the shape of a parabola. So it will gather all of that starlight and focus it onto one point. And then you can put an eyepiece at this point. Another way to use this parabolic reflector idea is backwards. If you want to create a beam of light going outwards, you can do that by having a parabolic mirror and then put a lamp at the focus. All of the light beams that are coming out of your lamp will bounce off of your parabolic reflector and all end up going in the same direction.